Okay. So actually that's been disabled.
Oh, okay. Well, I am not the host, Kelly. Does it work now?
Let me try. Not yet, but
No.
we can wait. Okay, will do. Thanks. Okay. Okay.
All right. I'm going to give everyone another couple minutes. Even though we're on Zoom, everyone's still 2 minutes late usually.
So it's the right screen that I'm showing, right? It's the.
Yes, that looks perfect.
Thank you.
Oh, Mikael, do I see you there? Are you actually there?
Yeah, I'm here.
Are you doing the seminars for the summer?
I do not know. I agreed to do seminars for next year and then have not gotten any other information. Maybe
Okay.
I should be seeking it, but we can
Okay.
talk. Yeah.
Okay, since this is the last one, if there were going to be seminars in the summer, I wanted to announce it. But if there's nothing planned, then.
Oh, maybe I should get on that. Okay. I'll probably reach out to you soon and try to get the skinny on.
Okay.
All right.
All right. Well, in that case, as people continue to leak in, I welcome everyone to the last iQuiz seminar of this academic year. We are excited to have Jen Choy with us from the University of Wisconsin. And Jen did her PhD at Harvard and then went on to work at Draper for a few years before joining the engineering physics department at Madison in the fall of 19. And so today she's going to be telling us about photonic engineering of atomic sensors. And please, everyone, if you've got questions, either put them in the chat or pipe up, and we can have a nice discussion, hopefully.
Thank you very much, Elizabeth, for the introduction and also for inviting me to visit UIUC virtually. I look forward to meetings with hopefully many of you, as well as the discussion during the talk. So please feel free to interrupt with questions. So in today's talk, I'd like to first talk about some basic concepts behind atom-based sensing, of which a major component is interactions between atoms and photons. I will try to illustrate some of the benefits and challenges of developing a futable atomic sensor by describing the development of a cold atom accelerometer gyroscope, which I participated in as a staff scientist while I was at Draper Lab. Then finally, I'd like to talk about our recent work at UW-Madison on applying integrated nanophotonics in order to improve the performance and functionality of atomic sensors. So this work, the development of a cold atom accelerometer and gyroscope work was primarily done at Draper. And it was a project that was funded by DARPA under the C-SCAN program. While at UW-Madison, I'm lucky to have a team of very talented and motivated students and postdocs who are helping to build our lab. So for today, most of the work that I will talk about were led by students Shuting Yang and Sarah Francis, as well as Dr. Miriam Benalichla, whereas Ricardo and Miriam are working on some of the developments with sensing applications of color sensors in diamond, which unfortunately I won't get to today. Okay, so quantum sensors, in the most basic sense, they rely on measurements of quantized energy transitions that you can find in atoms. And these include optical and microwave transitions, and you utilize the sensitivity of these transitions to physical perturbations in the environment in order to operate the sensor. And in particular, alkali atoms such as rubidium and cesium, which have once valence electrons, are often used for atomic sensing because their energy structures are pretty simple. This here is an example of a rubidium-87 energy transition map. So you have electronic energies that are whose orbital configuration lead to near-infrared optical transitions, which you can readily probe using semiconductor lasers. And then you have interactions between the nucleus and valence electron, which lead to hyperfine transitions that span essentially megahertz to gigahertz wavelengths. These transitions can in turn be affected by presence of magnetic field by the Seymour effect, which is the basis of how you would use atoms to measure magnetic fields. And these transitions between atomic electron energy levels are especially appealing for precision measurements because atoms in a vacuum enclosure, they are isolated from the environment, and they behave more or less independently and identically for atoms in the same species. So you can expect pretty stable behavior from atoms. You can also make ensemble measurements in atoms and be able to infer the identical sort of interactions of each individual atoms with the environment. So you get a pretty good signal to noise in your measurement. In addition, the transitions, these electronic transitions, they can correspond to fairly high frequencies, which in turn lead to high measurement resolution. So all these enable pretty sensitive and precise measurements for time and frequency, in which you can get uncertainty in a second, at a second of essentially below 10 to the minus 15 seconds. And then you can get, you can measure very tiny magnetic fields, so down to below a femtotesla sensitivity. And then in the case of inertial motion, you can measure very small changes in gravity below these are 10 to minus 9 times Earth's gravity at about a second. So the common thread in all these atom-based quantum sensor is that you need effective atom-photon interactions to make them work. So a couple of atom-photon interactions that are common in pretty much all quantum measurements include absorption and emission processes, in which you need resonant light to excite atomic electrons to higher energy levels, after which you can they can undergo spontaneous emission, so you measure the fluorescence, and this allows you to basically both detect the presence of the atoms as well as the particular quantum state that the atom is in. And you can also utilize this process for stimulated emissions, in which electrons are driven to coherently oscillate between energy levels. And you also, at the beginning of every measurement, it is desirable to put all the atoms into a particular quantum state. And the process of optical pumping is a mean by which you can do that. So it refers to sort of continuous selective excitation of a optical transition in order to populate electrons in a particular preferential hyperfine state. And then finally, you can utilize the momentum exchange between atoms and photons in order to cool atomic samples. So there are many applications of atomic sensors, and they basically span different scales and different sort of application spaces. So on the larger end, you can have laboratory scale experiments that serve as essentially standards of time and frequency. Currently, how we define time in the United States, for example, is based on a cesium fountain clock at NIST. You can our communication system and the GPS satellite constellation also critically rely on onboard atomic clocks in order to keep stable time, as well as broadcast signal sort of back to Earth in order for for accurate positioning during the triangulation process. The broadcasting of an accurate time signal is a major part of that. And you can also use atomic sensors to test fundamental physics, such as the equivalence principle of gravitational inertial mass, as well as search for fundamental constants. And on the other end, you can also think about taking these atomic sensors out of the lab and make sort of fieldable sensors. And since atoms can be sensitive to many things, you can make sensors of electromagnetic fields, as well as inertial forces. And with magnetic field detection, for example, you can utilize the sensitivity of atomic sensors to measure geomagnetic signals. So this here is an image of an aerial magnetic survey map, actually done using atomic magnetometers. So you just mount that onto a plane and then fly over a terrain and measure the associated magnetic field variations over that terrain. You can also use sensitive atomic magnetometers to measure small signals from the brain, and other biomagnetic signals. And in the measurement of inertial forces, a major application, and one that I will talk about shortly, is they're using navigation system to essentially utilize the sensitivity of atoms to inertial forces to build accelerometers and gyroscopes. So having talked about some of the background behind atomic sensors, now I want to delve into a specific example, which is the development of an inertial sensor, which relies on, has all the common elements of in the atom-photon interactions that I talked about, and also is a good example that illustrates why an atomic sensor might be useful, and also some of the challenges that are involved in taking these sensors out of the lab. So first, let's start with what is the measurement of inertial motion. So you're trying to sense either linear acceleration and or rotational motion. And typically the easiest way to do that is to drop something, and that this something that you drop is typically called a proof mass, and measure how that moves as a function of time. So you measure its displacement. So in a classical sense, you have, and the proof mass typically in a mechanical sensor tethered to some sort of case or walls, and you measure the movement of this proof mass in response to inertial input. And because the proof mass has to be tethered, so you have to worry a little bit about frictional forces between the proof mass and the tethers and with the wall. And in addition, you would ideally want your proof mass to be kind of indistinguishable from sensor to sensor. So any variability in manufacturing will lead to essentially variability in your sensor response. And then you can, another concern is the sensor's response to a changing environment. So for example, changing temperature, how that would affect the displacements of the proof mass in response to the external input. On the other hand, with atoms, you have pretty much a frictionless, reproducible, and identical proof mass, especially if you can trap the atoms to a low temperature. So you essentially just have a ball of these sort of frictionless proof masses, which then provides you, in combination with the fact that the physical properties are pretty stable when isolated, gives you both high sensitivity as well as stability in the response. So this is sort of the most ideal case and why people were interested in using atoms to measure motion in the first place. But then there are, right off the bat, some concerns once you start implementing it, which is typically you need lasers to, and many of them, and as well as a lot of electronics to really make an atomic experiment work, especially one that involves cooling atoms. And you sometimes will need time, in every experiment, you need time to cool down atoms. So then you have a data rate concern. So are you going to spend part of your experiment cooling down atoms and therefore not sensitive to the motion that you're trying to sense? So there's sort of bandwidth and data rate concerns. And then finally, what happens if you take a vessel that contains the atoms to outside the lab? Is it going to still perform the same way as in the case that where you have your environmental sort of well under control? So these are questions that we're going to try to explore in this project. So first, how are we going to do inertial sensing with atoms, and in particular, how we can back out both acceleration and rotation rates. So let's consider two atomic clouds that within an enclosed vessel, this chamber that I show in this box here, that we throw towards each other at some speed v. So if the whole system is at rest, then you basically expect kind of a flat trajectory of these two atomic clouds where they just kind of exchange position. In the case where you have your case under acceleration in a direction that's perpendicular to your launch direction, then you actually expect the two clouds to group. In this case, if the acceleration is sort of in this direction here, but then they're going to be drooping in the same direction. In the case of a rotation along a direction that's orthogonal to the launch direction, then due to the Coriolis effect, you then actually see deflection of these two clouds in opposite direction. So if you measure then the displacement of these clouds from their initial position beginning from the beginning to the end of their trajectory, then you can relate that to acceleration as well as rotation rate. So in the case of acceleration, because the two clouds are drooping in the same direction, you can simply sum the displacement, and that's equivalent to your acceleration rate times t squared, where t is essentially the time of flight, the time that the clouds sort of spent in their trajectory. And because in the case of rotation, you have opposite deflection, you can then just measure these deflections and take their difference. And that corresponds to essentially the cross product of your rotational rate and the launch velocity times t squared. So right off the bat, we can see that if you want to build a very, very sensitive sensor, you want a very long time of flight. And that in turn scales with the size of the apparatus. If you want the utmost sensitivity, you then probably want to build as big a chamber as possible that provides the atoms to have the means to have a long time of flight through a long trajectory. That in turn then means that there's a trade-off between how mobile a certain experimental apparatus is and how sensitive it is going to get. And then another consequence of this t-square scaling is that in order to get a long time of flight, you want the atoms to be able to maintain their spatial, the atomic cloud to be able to maintain their coherence, and therefore, in general, cold atoms are preferred for a longer dwell time. So let's talk about how we're going to measure these displacements. We use a technique known as atom interferometry, which is analogous to the Mach-Zehnder interferometer in optics. So we're implementing instead of an optical interferometer, a meta wave interferometer, where we're treating atoms, each individual atom as a meta wave. Because as we toss the atomic cloud at some velocity v, that means that we're imparting this atomic wave with some initial momentum. So here we're looking at a map of the vertical position of the atomic wave as a function of its longitudinal position. So we're tossing the atoms from left to right here. So initially you start with an atomic wave with some momentum, and then we impart some momentum via a component that is a beam splitter, which then splits apart the wave packet. So you have part of the wave packet with some momentum cake, h bar k, that kicks it up, and then the outer part maintains on its flat trajectory. Then you have the waves pass through mirrors, which then deflect the waves, so that this upper arm then the trajectory flattens, and then the lower arm gets receive this momentum cake, h bar k. And then finally, you add another beam splitter, which mixes the waves, and from that you get an interference. And this interference contains within it the phase difference between this upper and lower trajectory, which in turn is related to the path length difference between the upper and lower arm. And we're going to talk about how we implement these beam splitter and mirrors later, but essentially we're using laser pulses in order to do that, using two photon Raman transitions. Okay, so in the case where you have no inertial motion, that you basically, the path that the atomic wave packet takes is that parallelogram, but then the minute you introduce external motion, you have essentially a difference in the path length of the upper versus lower arm. So then the trajectory kind of warps in the manner that's sort of shown here. And so if you measure this path length difference and compare the case of no motion versus sort of with inertial input, you then see a change in the phase. And this change in the phase in turn is going to correspond to the change in displacement. And we know that that's related to the acceleration and rotation rate. So therefore, that's the same goes with the phase response, which includes a sum of the contribution from acceleration. So this is all to kind of the first order contribution from this inertial rates. So to the first order, you have then just the dot products of your wave factor, your matter wave factor, and your acceleration rate times t squared, and then the contribution from the rotation rate is also the dot product of your wave factor with this cross product of the rotation rates and launch velocity times the square of the time of flight. And here, the time of flight is just going to be your launch velocity times the length of each of these segments. And so if I want to, in one measurement, be able to get both acceleration and rotation input, that's hard, right? Because then you can't really disambiguate between the contribution from acceleration and rotation. So the way we do that is we perform still a single simultaneous measurement on two atom interferometers, in which in one case, you reverse the sign of this velocity. And so you have two atom interferometers in which you're launching from opposite directions. And so then at the end of that measurement, you make two phase measurements at either end. And you sum those phases together, and that corresponds to your acceleration input. And then you take the difference of those phases, and that gives you rotation. And so what I've shown here is we're still thinking about the case where you're dealing with one atom at the time, but because the atom's response is going to be identical, it provided that they're well isolated and non-interacting. So what we really wanted to get a big signal is simultaneously have about 10 million atom interferometers going at a time, all happening within the same cold atomic clouds. So this here is how we implemented such a system at Draper. We used rubidium-85 in this case, and we had a custom-made chamber from Coquana, where this glass portion is where all the atoms reside, and the baseline, the trajectory of the atom is going to take place within about a 6 centimeter distance here. And where we're trapping the atoms actually are indicated in the in where you can observe these trapping coils. So we trap atoms at these sort of distal ends, toss them towards each other during the experiment, and then we do the measurement at these opposite spots. So in order to implement this, we need, because we're cooling atoms, we need a pretty low pressure. So we needed to use an ion pump that's located here. There's some concern that because of the ion pumps that we're using requiring a DC magnet, that it's going to affect the performance of the atom. So what you see here is the ion pump being housed in a magnetic shield, and it's also offset through this region here with the right angle neck from where all the sensing is taking place. So you have the opportunity to both offset where the where the DC magnet is going to be, as well as opportunity to put additional shielding around the atoms. So this here is just where the sensing occurs. And we still need to bring in optical beams to essentially cool the atoms as well as measure them. So this here is a picture, a false color picture of what happens after you turn on all the trapping beams. So these are two rubidium magneto-optical traps that they're not terribly cold, so they're just about tens of microkelvin, each probably containing about 100,000 atoms or so. So the first part of the sequence involves cooling and trapping atoms, and there we send in essentially 3 orthogonal pairs of oppositely directed beams, and also turn on the quadrupole magnetic field to trap atoms at these sites. Then we turn off the magnetic field coils so that atoms can be freely moving. And then we also utilize the Doppler's effect and shift the frequency of the trapping beams to essentially throw the atoms towards each other. And the launch velocity in turn is going to depend on the detuning of these laser beams sort of relative to each other. So for the kind of megahertz level frequency difference we use, the atoms will launch at a few meters per second, which means that given that this roughly 5 to 6 centimeter separation between these trapping sites means that we'll have about 10 milliseconds in order to complete the trajectory of the atoms from one site to another during our measurement. So this also then sets the sensitivity of our sensor. And this is a relatively, I guess, flexible system in that we can control by controlling the laser detuning, we can control the launch velocity and therefore control this dwell time. So we can explore a regime of not very sensitive or very, very short dwell times to a little bit more sensitive. But there's ultimately a limit to how slow you can launch these before you really see significant effect of the atoms being affected by gravity as it arrives at the other launch site. So there's a limit to that, but then we can actually explore a range of sensitivity in this setup. So at the start of the launch, we also need to prepare all the atoms into an initial quantum state, and we do this with optical pumping. And in this case, we do it with beams that are directed at in this direction. And there we also needed bias fields, which are applied by these printed circuit boards here. So as mentioned earlier, we needed to perform atom optics, which is in which we need to split apart wave packets with beam splitters and apply essentially the analog of mirrors to these matter waves. And the way we did that, instead of with physical gratings, we use light pulse Raman pulses. So we pick the transitions from the hyperfine states of the atoms to a virtual excited state. And we needed 2 colors of light in this case, basically with the difference of the 2 colors being equivalent to the hyperfine difference. And in addition to getting the frequency right, we also needed the beams to be, the Raman beams to be at the right configuration. So the whole purpose of this is to be able to do inertial sensing, and therefore the relative arrangement of the beam matters a lot. So in this case, you actually want the photons to be the photons that it indicates as omega-1 and omega-2 to be oppositely directed. And the reason is that is the following. So if you assume that you're starting with your atom is initially populating the F = 3 state, so you come in with these oppositely directed Raman photons, which then leads to excitation into this virtual energy level. And at that point, you then get a momentum cake in the direction that's sort of opposite to where you absorb that initial photon from the Raman beam. And then it's sort of all, the process is all simultaneously. It's not sort of stepwise like what I'm describing, but in order to go back down, you undergo stimulated emission, and you basically need to have the other photon, this omega-2, stimulate the emission of the electron back to the F = 2 state. And when that happens, your momentum cake ends up being in the same direction of your initial momentum cake. so that if you undergo this Raman interaction overall, you will actually get a momentum kick of 2h bar k, sort of such as the case shown here. And you can make a similar argument for atoms that are starting at f equals 2. So basically, you can utilize this to implement your beam splitter and mirror, and you do this by timing your Raman pulse. So the probability of the atoms being in a particular state is going to depend on how long you leave that light pulse on. So if you leave on long enough so that you have essentially 50% probability of being in f equals 2 state and in f equals 3 state, then you have implemented a beam splitter. If your probability goes to 1 and transitions from one state to another, then you have a mirror pulse. So we implemented the Raman interferometry at essentially different locations of these atom clouds in their trajectory. So it's just one shown here. And then finally, we do state detection, where we're just sending in light pulses to excite fluorescence from these atoms. And we excite them in particular frequency so that the amount of fluorescence corresponds to the number of atoms in a particular energy state. And we use that information then to tell us the number of atoms in a particular energy state. And that in turn gives us information about the phase of the interferometer. And then finally, at the other end of the launch site, we actually turn on the magnetic field coils again and turn on the trapping beams again. So what this allows us to do is that at the end of the trajectory, the relative density, atomic density at these sites is still relatively high in comparison to background pressure. And so this allows us to load atoms much faster. And so instead of having a relatively slow setup where the trapping takes 1 or 2 seconds at a time from background, we actually are able to maintain steady state atomic population with a trapping cycle of about 5 to 10 milliseconds. And so this in turn allows us to have relatively high data rates. Routinely over 30 hertz, we can probably push it up to about 60 hertz, even though at that point you start really losing atomic population, which means that you have a possibility of being able to capture your inertial input rate much faster. So these are better suited for dynamic environments, even though you're kind of trading off in terms of sensitivity. So I guess are there questions up to this point before I talk about some of the experimental validation of this technique? Okay. If not, so this is what we've built. And this here is an integrated sensor with 4 degrees of freedom, which means that you have two degrees of freedom in your acceleration sensitivity, linear acceleration sensitivity. And then you also are sensitive to 2 different axes of rotation. And so this here pretty much has everything that you need to run all these 4 degrees of freedom inertial sensor, with the exception that, so this thick cable bundle actually does go to a bunch of power supplies. They're all like linear power supplies. And then also there's an Ethernet cable that goes into a computer that controls the experiment. But most of what you see here actually involves the lasers that you need to generate all the right frequency to do the cooling and interferometry. So it's about, I would say, 70% lasers, a bunch of electronics that we just kind of end up having hanging around this frame. The actual where the sensing occurs is inside this optical assembly here, which mostly consists of passive optics. So we use fibers that route light from the laser systems into this magnetically shielded optical assembly, which contains 2 vacuum chamber, with each chamber handling sort of 2 degrees of freedom of inertial sensitivity. And they actually also arrange in a back-to-back fashion, the idea being that you can then subtract out the sensor output to get rid of some of the common mode noise. And the optical assembly looks like this, but where you have mostly passive optics that route the beam and also polarize the beams to give it the right polarization. The actual sensing happens in this small comparatively much smaller volume in this vacuum.
Hey, Jen, before you go on from this awesome picture, Kent has a question of how many different laser frequencies do you use per measurement cycle?
Yeah, good question. I have to think about. So we basically we ended up using I think we have about 3. We ended up using 4 lasers here, and we don't necessarily need to use 4 lasers. And the reason why we used 4 was we didn't want to change the lock frequency of the lasers too much here. But then we basically need one. I consider one set of frequencies for cooling as well as for launching. So you can use sort of phase locking and frequency shifting of the lock point to help you get to all that frequencies. You also need to apply a some kind of either via some modulation approach or add another laser that's just dedicated for repumping the atoms so that you don't lose atoms to dark states. You need essentially 2 distinct frequencies for your Raman 2 photon Raman transitions, even though you could technically still generate that with a single laser, and then you just apply modulation to get to the right separation. But probably the more efficient way is to actually use 2 separate sources. And then we have one additional laser for state preparation, but then that actually you can generate using your cooling beam just by shifting the frequency. So I would say probably at minimum, so there are schemes that involve just using a single laser. You just basically build in that frequency agility. You just keep shifting frequencies during the cycle. In this case, we didn't take that approach, but yeah, I think there are quite a few colors that you do need to hit, about at least 4 to 5, but you can either accomplish that with all separate lasers or with a single laser.
If I'm looking at this picture here on the right, how many physical beam paths are there trying to hit this?
Yeah, so we have, so another choice that we made was that we didn't use any reflecting optics. We only use refracting optics, and that turned out to be a good design choice for minimizing some of the impact of vibrations onto the beam paths. But we have essentially 6 beams directing into the cell for cooling of the two sites. So I'm talking about each bench. So we have 2 benches here. The other one is like upside down for the back-to-back sensor. But in this top image here, we have essentially 6 beams going in. We don't see the vertical ones that are going up and down. Actually, that one is retroreflected. And then we also have state preparation, which are going in this direction. And then we have the Raman beams, which actually, I don't have a zoom in picture here. We built essentially in a little optical Mach center interferometer with essentially 3 parallel beams in order to essentially set our inertial sensitive axis, sending in Raman beams sort of through the middle of the cell here.
And then which way do you do the imaging?
We do. Oh, thank you for asking that, because yeah, what I haven't mentioned is the imaging part, which actually I'm wondering if I can. Yeah, you can kind of see it here. This is a better picture. So we use one of the cooling beams to excite the atoms, and then we use a parabolic mirror here to. So then the focal point of that mirror is here. So it collects. Yeah, it's not a very terribly big solid angle, but we collect the fluorescence here in this angle, and then we have an integrated detector here that basically is a tiny detector that is aligned relative to this parabolic mirror that basically does the detection.
Thanks.
Thank you. Yeah, so aligning this took some time, and to be honest, at the beginning of this whole endeavor, we were envisioning a much smaller sensor, and we were also exploring the possibility of using some more integrated, not just sort of chip scale components, but maybe even one step simpler than that, just micro optics to implement this. But it ended up being that we, due to sort of the timeline as well as sort of the tools of technologies available to us, ended up a brute force approach was what we ended up going with. And so we did put in some thoughts in definitely minimizing potential thermal and mechanical effects on these optics. But then it really was a brute force approach of sort of cramming bulk optics into as small a volume as possible. So let's talk a little bit about how well these sensors work. So this is our sensor package that we mount on a vibration isolation isolated platform, this -K, and then on top of that, it sits on a pier that's actually directly connected to the bedrock of Cambridge. And here we have the acceleration sensitive axis parallel to the ground, and then the rotation axis in this case is pointing up. So the projection of Earth's rotation rate based on the latitude onto in Cambridge, Massachusetts, onto our rotation sensitive axis about 10.5 degrees per hour. So that's what we're expecting to measure in the static measurements. And so we basically took a time trace of our acceleration signal as a function of time. And then we generate these Ellen deviation plots, which basically looks like correlation of a little different integration time within that time trace, and see how the sensor drifts as a function of time. So in the case where you have a very, very stable sensor and you're just limited by, let's say, white noise, in the short term, what you expect is this correlation, correlation function to essentially average down, and which is what you do see initially. So this left plot here is our acceleration measurement, and the right plot here is a rotation measurement. So you see this initial averaging down due to white noise, in particular velocity, random walk, as an angle random walk. So the rates are limited by white noise, and then therefore when you integrate that, you get a random walk. But then our sensor isn't as stable as touted because of some of the residual motion on the platform, as well as the fact that at the time that we took this measurement, we have not stabilized our Raman beam. So there were some power variations that led to essentially shift in the sensitivity. So we ended up not having a super stable, so it averages down to about 100 seconds. And then in some cases it goes back up, in some cases it flickers. But then your overall accuracy is still pretty much as predicted based on the size of the apparatus. So we have an overall about below 1 micro G accuracy, in where G is 9.8 times meters per second squared. And it's about 1,000 times better than what you expect with commercial devices. And this degree of accuracy is also good enough, for example, to tell gravity difference between sort of floors of a building. And we also started doing some small dynamic measurements where we are just applying this formula here to infer acceleration and rotation rates. So we can apply small tilts to the platform. And here what I did was literally put washers on one side of the platform. And with each washer, you actually see, due to the damping response of the mechanical frame, you actually see a little bit of ringing, as well as of the vibration isolation platform. But then here, so we're plotting acceleration as a function of time as I put these washers on and remove them. And here I've co-mounted a classical MEMS accelerometer with the atomic accelerometer, and we show that the response actually matched pretty nicely with just applying a simple analytic calculation. And then you do the same with rotation, applying very gentle rotation, and show that the atomic response matches very well with the classical case. And so here you notice that I'm applying very, very small rates to start, and that's actually by design. And the reason is that ultimately, because you're doing a phase measurement, you always will have a problem of not knowing what fringe you're on. So you make a phase measurement, you get a phase that corresponds to an inertial input, but then you don't know whether this phase is the value that you measure, or if it is that value plus 2 pi times n. And so you always end up having this problem with atom interferometers. It gets worse the more sensitive you get. So as you increase this dwell time, then that range to 2 pi range corresponds to a smaller acceleration and rotation input. And for a typical dwell time in our experiment of about 7.5 milliseconds, then your acceleration range is actually pretty small, like it's about 360 micro G, and then your rotation range is about 130 degrees per hour. And so then if you have a 10 degrees per second rotation, which actually, if you just visualize it, doesn't seem very fast. That's about 1,000 fringes that you would have gone through. And this here is an example of that. So the top plot is the acceleration input as a function of time. So you're wiggling the setup. And then what you actually measure on the atom interferometer is just noise, because you're not able to really disambiguate which fringe that you're on. And so in order to do that, you can use the classical sensor to help you find the right fringe. And that's exactly what we've done. We collect data from both the classical sensor and atomic sensor, and use the classical sensor to find us put us at the right fringe. And then we then interpret the data from the atomic interferometer properly based on that. And so this, we were able to apply, with this, we were able to apply larger acceleration rates. So this here, the experiment itself was kind of crazy. We, because of how heavy that whole apparatus is, we actually got riggers to come in to move the sensor onto this rate table here. So rate table is a pretty common platform that's being used to measure inertial sensors. So in this case, you have a degree of freedom where you can rotate this basically in this direction. So that you're projecting different amounts of Earth's gravity onto the acceleration axis. And then when you do that and you compare the output of the atoms and the MEMS, you see a very linear response, which is what you want and expect. And the other thing that we did was we varied the sensitivity of the interferometer with different dwell times to show that that response still matches quite well. So here in this case, we didn't push it too far because we were a little bit worried about, things catastrophically breaking. So we were only tilting it by about like 15 degrees or so. We were able to apply much larger rates with the rotation on this rate table. So here we are essentially just applying sort of half circle motions at different rates, and going from very, very small rates to about 10 degrees per second. Spending about sort of a few cycles at a particular rate. So we start with very, very small rates that you zoom in, you'll see the response. The dotted line here indicates the full 2 pi range. So basically we show that with this sort of combination of classical and atomic sensor, we could really catch the right fringe. And then as you apply larger rates, you can measure these larger rates beyond beyond 2 pi, and we show that for a single continuous measurement, so you're applying variable rates, you can actually catch all the inputs. So the blue here is the atomic gyroscope. It's a little bit lower noise seeming from this time trace here, and the red here is actually a fiber optic gyroscope that we mount at the same time. And the other nice thing about this system is that we can show that the sensitivity of this gyroscope response, it's pretty stable to the input rate, meaning the scaling of particular input rate correspond to a particular gyroscope response is very stable. And the way you measure that is by switching the direction of the rate. So you switch from positive rotation to negative rotation rate, and then you take that difference of the response and plot as a function of time, and that's stable to about 150 parts per million. And I think this is actually limited by the test that we did. So we can take this one step further, which is to apply like a live feedback of this interferometer phase. And there, what you do is to use a field programmable gate array, where you collect data from both the classical and atomic sensor, and you actually compute that inertial phase corresponding to the classical output live, and then apply a phase correction in your Raman pulse. And we show that you can actually get that to work sort of in closed loop and to real life correction. So here we're plotting again acceleration as a function of time, where I'm just sort of pretty robustly like shaking the platform. And the applied acceleration is what we're reading from the classical sensor. That's the one shown in blue here. The dotted lines is basically what one fringe could correspond to. And then we were able to show that we are our residual acceleration of the atomic sensor is actually very, very small. So we're able to catch all of that. And so what this is a vibration noise eater. You can think of it for an atom, where you can suppress the acceleration-induced phase response by more than 700 times. And as for why it's useful, you can think of what the residual response really means. So in the case that the atoms are more stable than the classical sensor, this residual response means it's basically all the small errors that are provided by the classical sensor. So you can essentially use this residual phase to correct for small and presumably pretty slow drifts in the classical sensor, much like how an atomic clock works. There are additional, so we were running maybe a little short on time here, but there are a couple of other sort of limits that this type of sensor has on the rotational rates that you can measure. And actually, this one in particular is due to atom temperature, where because you don't have a single velocity that's associated with the, you have a finite atom temperature, which means that you have a velocity distribution. This on top of what your launch velocity is. If the larger that distribution is, the more, that means that you have the opportunity of essentially generating tiny little interferometers based on that velocity distribution. So you have essentially shearing of the interferometer phase under that especially gets significant under high rotation rates because of this term here. So your fringes basically look washed out, and therefore you experience a contrast loss as a function of rotation. And this effect gets worse as you increase your atom temperature. So this is what we modeled and expect and has been observed in other experiments in the literature. And this is actually what we also measured in our experiments. It matches very well with our model. And in order to really mitigate this effect, there are a few things you can do. One is you can vary this dwell time. So depending on what your expected rotation rate is, you can always make it longer or shorter in order to sort of mitigate this contrast loss. And you can use a gimbal essentially to correct for large rotational motion and use atoms only to measure small rates. And then you can also measure this phase shear in order to recover contrast loss. So to summarize this part of the talk, what we developed at Draper is pretty comparable in terms of size and complexity to some of the cold atom inertial sensors, for example, with the ones from muquans and some of the developments in academia on a mobile-ish, I guess, inertial sensor. And the benefits you get are from atoms is sensitivity and stability, and the fact that you can pretty easily match your results with an analytic model that's simple. And in that case, the suitable use cases are pretty slow platforms, such as the case in space or water. And if you really need to capture dynamics, then you can use a gimbal, or you can use your atoms in conjunction with classical sensors. But then the challenges are that systems are just always very big and complicated, and they're costly and time consuming to make, and then you experience performance degradation during motion. So in the last few moments, I want to talk about some of the things that we're interested in to really take this technology to the next step. And one of them is essentially investigating chip scale technologies for atomic sensors. And a lot of that is in photonic engineering, in particular of the atom-photon interface by developing integrated components that can effectively talk to atoms, and also by making more miniaturized optical sources and active sources, active components like modulators. So there's been a lot of exciting work in applying integrated photonics for atoms. These include sort of some of the chip scale tetrahedral magneto-optical traps, as well as applications. We're starting to see application of metasurface components, which are sort of these planar wavelength scattering elements, which geometry can help you tailor a particular desired phase delay onto an incoming beam. So that's what our lab's been working on for since we started, is to explore applying, designing, and as well as integrating metasurfaces for polarization control of atoms. And so the first case that we are starting to explore is a simpler case where if you want to trap atoms, often and if you want to do Raman interferometry, often this beam steering is a big concern. And so to make things simple, we're just starting with atomic vapor and looking at the sensing of magnetic field by atomic vapor and applying sort of these flat optical components to demonstrate that you can integrate photonics with atoms. And so components that we started building include a dichroic wave plate that basically generates circularized light that can allow you to optically pump atoms, and then a chip scale polarimeter that allows you to essentially measure the polarization state, the optical polarization state of a probe beam, which in turn has encoded with it information about the magnetic field. And so skipping through sort of how we design these, and I'm happy to talk more about it if there's a Q&A session. But we've designed these components for 780 nanometers, both quarter wave plates. This is work mostly done by Shooting, Miriam, and Sarah in our group. And then this here is a polarizing beam splitter where we can demonstrate that if you're an input beam, the transmitted beam is going to be routed in a direction that's based on the polarization input beam. So it basically functions as similarly to a polarizing beam splitter, a cube beam splitter. And we're been building up our test setup in the lab, and also while we're getting these devices fabricated, trying to model magnetometer response both in experiments and also analytically based on the projected performance of the photonic components. And hopefully we'll, in the coming months, we'll start seeing initial results. So I think maybe it's a good point to end my talk here. Hopefully that leaves a little bit of time for questions. And thank you very much for the opportunity to speak here.
Thanks for a great talk. That was super interesting.
Thank you.
Do people have questions before I ask my questions? Dante, you are muted. If you're
there we go, I'm muted. Hey, Professor Choy, thank you so much for this amazing talk. I actually had a question. When you think about using integrated photonics for these types of accelerometers and gyroscopes, what kind of new application spaces are you entering when you can miniaturize these things to these types of resolutions?
Yeah, so I think I guess the broader applications is, I think, the opportunity to potentially be able to more easily take these apparatus out of the lab, and it's not just a miniaturization gain. I think you actually get potential performance gain because you do notice especially with these like bulk components, if you're integrating them by brute force, the minute you introduce some mechanical strain or you change the temperature, you basically have shifts in the direction of the optical beam. Sometimes you see changes in the polarization performance as well. And so then that really limits the long-term stability. So I think one of the claims that, at least that I've been making, is that with this tighter integration, which can be afforded by these integrated components, that maybe you can mount directly inside the cell, or maybe incorporate as part of your vacuum VAXO, that you can have this more tightly integrated system would be inherently a little bit more stable. So maybe the longer term application would be a miniaturized navigator that you can put on a moving vehicle that can withstand some of the dynamics and without seeing the performance degradation. But on the other hand, there are potential potential drawbacks with, I think, the impact of using these nanophotonic components on the beam quality, for example, is kind of, the jury is still out, and a lot of sort of characterization needs to be done to really make sure that you're not trading off performance as well.
And just one quick follow-up. I mean, in the first half of your talk, when you're talking about the cold ions and how you were able to get resolutions that were 1,000 times commercial sensors in terms of like measuring the microgravity between floors, which is just kind of crazy. What, like, is there a need for that type of resolutional advance? Like, is there something, like, is this for like space technologies where we're flying like between planets or something? I don't know.
Yeah, that's a great question. So I think there's so being able to measure those tiny changes in gravity is useful from the standpoint of fundamental physics and sort of test of the equivalence principle. And there, the devices that I talked about, they're not ideal for that because they're probably too small and not sensitive enough. And there you really want
Oh,
giant
wow.
experiments that can really be able to tell the difference between very, very small separations. And so that's sort of one application. There's also geodesy, being able to better understand, the gravitational changes, of our planet.
Oh, wow.
And there you can use gravimeters. You can also use very, very sensitive clocks to do that. So this whole field, why, we do pretty well in our daily lives with GPS, right? With navigation, like why do we really need better sensors in most of what we do? And I think there's some concern, especially with our use of GPS, which inherently is a really, really tiny and low power signal, that there are times when we lose the signal. There are times when the signal can be jammed or spoofed. And so this basically it's not meant to replace any existing technology. It's meant to augment it, basically, in cases where you really care about having a continuous means of accurately being able to tell where you are. Then maybe some of these instruments that are supposed to be inherently stable will be great for it. I don't think they're ever going to be standalone instruments because of some of the drawbacks I mentioned, but you can potentially use these instruments, for example, to measure changes in gravity when you're on a plane, and then be able to match that with, a known gravitational map, so you can tell where you are, for example.
Oh, that'd be pretty cool. Thank you.
Thank you.
All right, anybody else? So I want to ask about the design of your metasurfaces for your integrated photonics.
Let's see, let's go back to that slide.
So this is super cool.
Thank you. Yeah. So I guess I can do. Would you like me to give a quick sort of?
That'd be great. Yeah.
So actually, we there's a lot of work over the last decade, exciting work on metasurfaces, and we're not inventing the wheel here. We are actually using some of the existing design principles. So this the method that we're using in particular involves a backpropagation of the desired vector field. So basically, we know what we want, let's say, at our detector, and we know the optical fields there on that plane. We then, just using Wave's equation backpropagate to where the metasurface is, and then we know what we need that metasurface to do and the phase that it needs to impart onto the incident field in order to generate the desired vector field at the output. And we're implementing this with elliptical posts, planar posts that are sitting on a transparent substrate, in which as you change the geometry of this post, you can then change the transmission and the phase of the incident wave. And so the first thing we do is a parameterization of these post parameters, let's say at a fixed periodicity and a fixed height that's set by whatever sample we have access to. In this case, we're mostly looking at silicon on sapphire substrates, silicon being like it's a high enough index and it's transparent enough at the wavelengths that we care about, which is 780 nanometers in this case. And so we then obtain by parameterizing just the elliptical parameters here, we can obtain phase and transmission coefficients as a function of the post radius. So that's sort of our library of our design tools, essentially. Then with this backpropagation method, we have this phase map that we then match with our library. And in the ideal case, we basically want to find like a region where you have a full 2 pi phase shift, so you can do anything that happens to have not a ton of transmission loss. So that's sort of the design trade-off, is to be able to find that sweet spot. And within that sweet spot, you look for geometric parameters that match your exact or discretized desired phase, and you populate your metasurface. And then we just do full wave simulation to sort of validate the response.
So you just declared silicon transparent at 780. Is there a reason? Is there a reason to use silicon as opposed to like silicon nitride or something that actually is transparent at 780?
We used silicon because we thought it would be, well, so first we have to be a little bit careful because at some point we also considered polysilicon, which would just give you larger losses. So you're going to get some loss. Actually, I think the designs that I've shown, I believe the transmission is about 85%. It's definitely, you're getting some material losses there, but it's, I guess, transparent enough in the sense that the high index gives you makes the design a little bit easier in finding that full tube high coverage. We are exploring, actually, not necessarily silicon nitride, which has an index of about 2. So
Yeah.
maybe like titanium dioxide, for example, might be. So yeah, there's definitely visible matter surface work using those materials that we probably should start looking into. It's just that to start, we picked this material.
So are you currently limited by the material loss or by fabrication imperfection?
Well, so we'll find out. I think we are able to get actually single crystalline silicon on sapphire, which is why we started doing some simulations on sapphire. So hopefully we won't get tons of absorption losses there. And we're just starting the process of doing fabrication on these. So I'm sure. So one big concern is we should probably iterate the design a little bit more to make it more fabricable, because right now the aspect ratio is we have 500 nanometers and about 80 nanometers in the starkest sort of aspect ratio that we have, which is a concern. We're not quite sure if we really can hit that, but we'll learn more as we sort of start this process.
Very cool.
Thank you.
All right. If there are no other questions, thank you so much for coming. It was
Thank you very
great
much.
talking to you. And thanks everyone for coming to our last seminar.